Okay guys, Assalamualaikum warahmatullahi wabarakatuh. Okay, 4.3 the orbital overlap and hybridization. Alright, so kita tengok dia punya learning outcome at the end of this topic. You all should be able to draw and describe the formation of sigma and pi bond from overlapping of orbital. Okay, alright. So valence bond theory describe the formation of covalent bond through overlapping of two neighboring atomic valence orbitals. The overlapping orbital contain a pair of electrons with opposite spin. Okay, form two type of bonds. Okay, so yang ni yang penting, sigma bond dan juga pi bond. So dia punya tanda untuk sigma bond seperti mana yang tertera dalam PowerPoint tu, and then the pi bond of course like that, and then sigma bond. What is it? The sigma bond? Sigma bond is a covalent bond formed from the overlapping of end to end of atomic orbital or neighboring atoms. And then overlapping of two s orbitals. So this is example s plus s. Okay, so itu merujuk kepada sigma bond lah, head to head lah ataupun end to end lah. Right, and then overlapping of s and p orbital. Alright, so p orbital dalam bentuk dumbbell, of course orbital s dalam bentuk spiral. So tambah antara dua tu, you akan dapat sigma bond. Right, overlapping between p orbital and p orbitals. Right, so p overlap dengan p untuk menjadi sigma bond end to end. So dia akan jadilah sigma bond. Alright, so example overlapping of two s orbital. Example adalah hydrogen. So kita tahu dia punya dia punya balance 1s and 1s. So apabila dia overlap, okay, so dalam bentuk spiral 1s, and then the other one spiral also 1s, so dia overlap untuk hasilkan sigma bond. Alright, okay, that one. Alright, done. Okay, you can tulis state lah. Alright. Okay, overlapping of orbital s and p orbital. Example hydrogen fluoride HF. Alright, hydrogen 1s. And then for the fluorine, dia adalah group number 17 and then period number 2. Of course, dia punya tu ada 2s2, 2p5. Okay, so itu merujuk kepada fluorine ya. Alright, orbital overlap diagram. So okay, so dapatlah you punya overlap between orbital s and orbital p. Okay guys, we go to the next example, overlapping of the p and the p orbitals. Example given here is the Cl2. Alright, Cl2. So we already know that the Cl elements situated in the periodic table in group 17 and period number 3. Right, so dia punya valence untuk Cl adalah 3s2, 3p5. Alright, and then alright, both. Alright, so we can draw the p orbital untuk Cl like that, and then the other p orbital untuk Cl, yeah, like that. Alright, and then you do the orbital overlap between those two Cl. Alright, so you akan dapat, okay, that one. Alright, so overlap. So this is the end-to-end overlap. So sigma bond. Alright, 3p, 3p. Cl, and then you state the sigma bond. Alright, and then how about the pi bond? A pi bond is a covalent bond formed from the side to side overlap of two p orbitals. Alright, and then Before this, you all already know that the orbital P consists of three. There is Px, Py, and Pz, right? Alright, so for the side to side overlap, so you will manage to get pi bond. Example for the P and P orbital overlap is nitrogen gas. Alright, so nitrogen is in period number 2 and group 15. Alright, so dia punya valence 2s2 to p3. Alright, the other nitrogen is 2s2 to p3. Alright, so you do the px over there, py over there, and pz. So before this, I already told you all that the px, py, and pz will be based to the x axis, y axis, and z axis. Alright. Okay, and then where is it? Okay, so that one is the px. Okay, the px, the blue color merujuk kepada x axis, the red color merujuk kepada the y axis. Alright, meanwhile for the green color merujuk for the pz. Alright, so alright, px, between px, that is the sigma bond. Alright, the first thing, the sigma bond, blue towards blue, and then red to red, that is the pi bond, the first pi bond, and the second pi bond, green to green color. Alright, so you manage to get the second pi bond. Alright, okay, that one is the sigma bond. Both of those two is the pi bond. Alright, so we go to the next lecture, lecture number 3, 4.4 intermolecular forces. So learning outcome here, you also be able to describe intermolecular forces, van der Waals forces, that is the dipole-dipole interaction or permanent dipole, London forces, or you can say dispersion forces. And the other one is the hydrogen bonding. Okay, introduction. Intermolecular forces are the attractive forces that exist between molecules. So for the intramolecular forces between HCl is the covalent bond. Alright, and then towards other HCl there is intermolecular attraction ataupun intermolecular forces. So attraction between HCl towards other HCl is weak, right? Okay, the other attraction. Alright, so that is the attraction. This is not the intramolecular forces. This is the intermolecular forces. Alright, so the intermolecular forces are very much weaker than covalent or ionic bond. Sorry guys. Alright, we go further. Alright, the structure of the intermolecular forces are responsible for the physical properties of simple molecular substances, such as melting and boiling point. Why? Why we must know the intermolecular forces, guys? Because we want to know about the boiling point, the melting point, and the physical property, and also the solubility. Alright, we are going to study two types of intermolecular forces. That is van der Waals forces. The other one is the hydrogen bond. So the van der Waals forces, two types of van der Waals forces. There is dipole-dipole forces and London forces, or we can say that dispersion forces. The intermolecular forces increase the strength according to the following. So London forces is the weakest, and then dipole-dipole forces is stronger compared to London forces. London forces and dipole-dipole forces are weaker compared to hydrogen bond. Alright, dipole-dipole forces. Attractive forces exist between neutral polar molecules. So before this, you all already do the lambda, right? You can draw the Lewis structure, the molecular geometry, the lambdas, the polarity, right? Alright, so at the polarity column, so you must know whether that molecule or ion is polar or non-polar. Okay. Okay, once you know that that molecule or ion is polar, so you can say between polar and non-polar molecule exist intermolecular forces. Intermolecular forces, that is dipole-dipole forces. Alright, the forces arise from the attraction between partial positive charge on one molecule and partial negative charge on the other molecule. Let's say we try to take a load of HCl. As you know, between the H and Cl, H is more less electronegative compared to Cl. Cl is more electronegative. Alright, so we can say the partially negative at the situated at the Cl, meanwhile partially positive situated at the H. Alright, between HCl to other HCl. Okay, so I draw to you all again. Where is it, the color? The color for this one, where is it? Where is it, guys? Okay, wait up. Okay, this one. Alright, so green color. Alright, so this is your molecule, right? And then you know the polarity of HCl is polar molecule, correct? Okay, this one is polar, so this is your bond dipole, so you can say HCl is polar molecule. Alright, polar between polar molecule, so this one is delta plus, this one is delta minus, according to their electronegativity. Alright, so between delta minus to delta plus, there is attraction. Alright, there is attraction, there is dipole forces. Alright, this one also there is dipole forces towards other HCl molecule. So for polar molecule there is we can say van der Waals forces, there is a dipole forces between non-polar molecule. Begitu juga towards H2S. This is the example of dipole forces between H2S towards other H2S. Alright. So predict whether this molecule is polar or non-polar. Once you manage to predict according to the bond dipole, is it cancel or not? So for this one, we know that H2S sorry guys, the bond dipole cannot cancel each other. It means S2S is polar molecule. So S2S towards other S2S, we can say there is polar molecule towards other polar molecule. So the intermolecular forces, there is dipole forces exist between them, right? Where is it? Okay, boleh ya? Alright. And then we go to the other one, the van der Waals forces, London forces, as is in all atom and molecule. Alright. So in average, the negative charge of the electrons in the atom or molecule is spread evenly around the nucleus. Right. And then at any instant, one side of the atom of molecule has higher electron density than the other side. Alright, ni maknanya dia bergerak lah ni. Kita ada electron, right, moving around the nucleus, right. So pada satu ketika, the density of negative charge is greater compared to itulah apa nama kita panggil ni, keberadaan elektron tu berada di sebelah pihak, pada sebelah side. So apabila elektron banyak sebelah situ, dia sekejap ni, so kita boleh nyata partially negatif dia akan terhasil kat situ, right. And then dah jadi delta minus, is mean the other side will be the delta plus, right. And this instant, the atom or molecule become a small instantaneous dipole, then induce a dipole on the neighboring atom and molecules. Okay, so you tengok kat sini, dia akan jadilah instantaneous dipole. Okay, this one for the non-polar molecule. Okay, where is it? Okay, so where is it, the intermolecular forces? This one. Due to electron refraction, instantaneous dipole on one atom can induce a similar dipole on the neighboring atom, which can cause the neighboring atom to be attracted to one another. Alright, kalau you tengok situ, instantaneous dipole and induced dipole. So situ data plus, data minus, data plus, data minus is mean dia adanya intermolecular forces lah kat situ. So this interaction is called the London forces or dispersion forces. So up to you lah. Up to you guys, whether you want to use London forces or dispersion forces, because those two terms is same meaning. Alright, and only significant when atoms are very close to one another. Example for the London forces. Okay, Cl2. Cl2 is one of the covalent bond, and we can see that Cl2 towards other Cl2. Okay, Cl2 is a non-polar molecule. So intermolecular forces between Cl2 towards other Cl2, only weak intermolecular forces, there is London forces. Alright. Okay, so this one is alright. Okay, so London forces. Alright. Okay, so London forces exist. Whether is it non-polar molecule? Yeah, exists London forces. Or polar molecule. Polar molecule also exists the London forces. Besides that, there is for the polar molecule there is a greater intermolecular forces between them. There is the dipole forces. All right. So we can say that the polar molecule has a greater boiling point or melting point compared to non-polar molecule. Alright. Okay. Now another example. State the type of intermolecular forces exists between each of the following molecule. So the first one, you must guess or must know whether the given molecule is polar or non-polar molecule. Given here is, okay guys, given here is BF3. So BF3 is a non-polar molecule. How do you know? Because the bond dipole can cancel each other. It means a non-polar molecule. So your mu will be 0, right? So between BH3 to another BH3, only London forces exist. Alright. How about carbon dioxide? So carbon dioxide, if you do the bond dipole, yeah, the bond dipole can cancel also each other. It means carbon dioxide is a non-polar molecule. So London forces exist between carbon dioxide towards other carbon dioxide. Alright, how about CaCl3? Alright guys, so this one, for the CaCl3, this is a polar molecule. Why? Because the bond dipole cannot cancel each other. It means between CaCl3 towards other CaCl3, there is intermolecular forces. What is it? The dipole forces. Alright. And then how about the example for the CCl4? CCl4, if you draw in the molecular geometry shape, so you will draw the bond dipole, and then lastly, yeah, you will find out that the bond dipole can cancel each other, right? So we can say that CCl4 is a non-polar molecule. It means CCl4 towards other CCl4, only London forces exist between them. All right. Okay. So we go to the hydrogen bond. Okay, what is a hydrogen bond? Is a strong attraction between the positively charged hydrogen atom of a molecule and the negatively charged electronegative atoms such as fluorine, oxygen, and nitrogen atom of another molecules. Alright, HF, one example. Okay, so delta plus, delta minus. HF, okay, delta plus, delta minus. Alright. So this one, okay, positively charged electronegative atom. So that one is the hydrogen bond. HF, towards other HF there is hydrogen bond, but HCl towards other HCl there is no hydrogen bond formed. Only dipole forces, guys. Please do remember, right? Alright, and then we go further. This is example of the hydrogen bond. Okay, water towards other water, there is one hydrogen bond. Ammonia towards other ammonia, there is hydrogen bond. Water towards ammonia, there is hydrogen bond. Okay, ammonia towards water, there is hydrogen bond. Hydrogen fluoride towards ammonia, there is hydrogen bond. And ammonia towards hydrogen fluoride also has hydrogen bond between them. Alright, so hydrogen bond in organic compound. So carboxylic acid, and there is the class of compound, right? Carboxylic acid. So carboxylic acid towards the other carboxylic acid, there is hydrogen bond exists between them. Alright, carboxylic acid, the class of compound. So the functional group will be carboxyl. Alright, R2O. Alright, and then alcohol class of compound are which class of compound? So the functional group will be hydroxyl. So alcohol towards other alcohol exists also the hydrogen bond. And then amine is the class of compound. Meanwhile, the functional group is the amino. So amino towards other amino, there is hydrogen bond. Alright, amine is the derivative of the ammonia. Alright, and then 4.5 and the metallic bond. Alright, so learning outcome at the end of session lesson, you all should be able to explain the formation of metallic bond by using the electron sheet model, and then B, explain the factors that affect the strength of metallic bond. Alright, metallic structure. In a metallic structure, metals atoms can be imagined as an array of positive ion immersed in a sea of delocalized valence electron. Metallic structure also known as electron sea models. Alright, so sea of electron positively charged metal ion. So the electron sea model as shown in the figure given in the PowerPoint slideshow. Alright, and then a metallic bond can be defined as the electrostatic force between the positively charged metal ion and the sea of the localized electron. Alright, so okay, that is the metallic bond. Alright, so this one is an example metallic bond for the sodium ion. Alright, so this one is 9 mole of sodium. So please draw 9 of Na plus, and please count the electron. Should be 9 electrons also. Jangan letak kurang elektron tu. Kalau 9 mol you pakai untuk sodium, it mean 9 mol juga elektron perlu ada dalam C model. Alright, pernah keluar dalam exam. Kalau you guna 3 mol, sepatutnya ada 3 elektron lah. Alright, so sini 9. So you kira lah. 1, 2, 3, 4, 5, 6, 7, 8, 9. It means betul. C electron of sodium. Alright, and then electron C model of magnesium. So you use how many mole of magnesium here? Berapa ni? Alright, 9 also. Magnesium situated in the periodic table group number 2, correct? So it means 2 valence electron for the magnesium. It means when you use 9 mole of magnesium atom or ion, it means 9 times 2, it means 18 electrons. So please calculate. The electron for the C model of magnesium should be 18 electron. Alright. Okay, and then metallic structure of the aluminium. Alright, you use 9 also. It means 9 times 3 is mean 37 electron. Alright guys, so continue later. Okay guys, I will continue again our lecture. Alright, so the properties of the metal in electron C models, metal ion can easily slide over each other to new relative position when a sufficient force is applied. Therefore, metal can have the ability to be deformed or pressed into different shape under compression. So this one is malleability, to be stretched or pulled into a wire, ductility. And then due to the presence of the delocalized electron, which can move freely over the entire metal, mobile electron can act as a charge carrier in the conduction of electricity, or in the hand you can say electrical conductor. And then B, energy carrier in the conduction of heat conductor. And then we go to the factors that affect the strength of metallic bond. So the strength of metallic bond depend on the number of valence electron and the size of positively charged metal ion. So strength of metallic bond is directly proportional to the number of valence electron and inversely proportional to the size of positively charged metal ion. Right? So strength of the metallic bond, which has higher bonding point between sodium and magnesium. Explain your answer. So sodium has 1 valence electron. Meanwhile, for the magnesium, it has 2 valence electron. They are according to their group, right? So you already know that sodium is group number 1, and meanwhile, magnesium is group number 2, right? Alright, and then the strength of the metallic bond is directly proportional to the number of valence electrons. It means magnesium has stronger metallic bonds compared to sodium. Therefore, magnesium has higher bonding point rather than sodium. Alright, and then strength of metallic bond size of positively charged metal ion, which has higher bonding point between sodium and potassium. Explain your answer. So this is the example for the same group, right? But different period. Sodium is period number 3, meanwhile potassium is in period number 4. Alright, both sodium and potassium has 1 valence electron. Why? Because group number 1, right? So sodium ion has smaller size than potassium ion. The strength of the metallic bond is inversely proportional to the size of positively charged metal ion. Therefore, we can see that sodium has stronger metallic bond than potassium. Therefore, sodium has higher bonding point than potassium. Alright, so guys, done for our lecture today. Next time I will go through about the new chapter. Okay guys, bye bye.